Thank you very much. I'm very happy to be here. It's my first time in Taiwan. As our chairman said, I'm deeply impressed. The two departments joined together to invite me here, the physics department and the philosophy department. And on top of that, a chemist is my chair. It's wonderful. Many universities that I know wouldn't be able to do something like that. So I'm very happy that you are able to do that. It's a little embarrassing to talk to my hosts because I know so little about your country, but I'm learning much. I learn about the complicated history of this country to Japan. I learn about the complicated relationship of this country to the continent. And it's very rewarding for me because I've been in Europe and the United States most of my life. And I'm starting to now learn more about this part of the world, which I find very fascinating. Now let's get on to the lecture. The subject of the lecture is what is science, and I'm going to deliver today what I call a short answer, but I will give you an overview of what I'm doing in all these two lectures, first of all, and then I'll tell you something what I do in the third one as well. First, here's the outline of the two talks. First, I'm dealing with the question itself, what is science? This is something which is quite uncommon for scientists, that you do spend some time just discussing the question itself, not answering it immediately, but first reflect upon the question. What does the question mean? What does it imply? What are certain contrasts, and so on and so forth. So I will first deal with the question itself, and I will present you some preliminaries, then I give you the short answer itself. So this is not a talk in continental philosophy where people discuss other texts and never answer questions. But I will give you an answer to the question and I will discuss that answer. I will then give you, and that is again of course more nearer to the continental tradition in philosophy, I will give you a little history of that answer. And then I will explicate the answer. This will be then the heavy part today. I will give some qualifications of this answer because one has to be quite careful with this answer. It's a very simple answer apparently, but if you look a little closer it's becoming quite complicated. Believe me, you will believe me by the end of the next lecture. Then of course some conceptual clarifications, that's always necessary in philosophy. And then an interesting question, quite a complicated one, will be how to argue for the answer. I'm not only just giving you the answer, but of course I'm trying to give you arguments why this is the right answer. But it will be quite complicated to find out what appropriate arguments are for this answer. And then tomorrow on Wednesday I'm going to speak about the justification of the answer in 9 steps. I don't know whether the number 9 has a special meaning in your traditions. Perhaps it has, 3 times 3. At any rate, it'll be 9 steps. I'll tell you why later. And then I will compare what I'm developing here with other positions, and then very traditionally I'll end with a summary. Okay, so let's start, and we first discuss the question, what is science? And I start with some historical preliminaries. The reason is I am not the first one who has asked this question and has tried to answer it. This is really the beginning of philosophy of science in Aristotle, of course. Everything starts in Aristotle, at least for Europeans. That may be different for you, but for Europeans it's quite clear it's got to start in Greek antiquity. That's perhaps a little Eurocentric. At any rate, I can't help it. So I will tell you the story, the history of the answers to the question, what is science, in a very schematic way. So professionals, historians of science will hate what I'm going to say. They hate that when philosophers do this rather schematic way of presenting a long and complicated, involved story, but philosophers love it usually, and what I'm trying to do is to get out the essential elements of answers, and I make a periodization by telling you it is really 4 different phases in this answer to the question of what is science. Now it starts, of course, as I said, in antiquity, and there's a continuity in antiquity until the 17th century, and the basic conviction was at that time that scientific knowledge is certain knowledge, and the certainty of that knowledge is established by proof. That's the idea. This ideal or idea of science is, of course, still vivid in mathematics. But it's not vivid any longer in the empirical sciences, but in mathematics you still have that same idea. Mathematical knowledge must be certain, and the certainty is established by proof. Of course, there are many problems involved, I'm not going to discuss them here, but that was the basic idea, and that was the basic idea not only for mathematics in antiquity and the Middle Ages, but also for what we call the empirical sciences. That is a little alien for us now. It's a little foreign. It's a strange idea to us, and that is because we have crossed 400 years in between, in which very much has happened, both in the sciences and in philosophy. Now, the second phase I'm putting between the 17th century until the second half of the 19th century, and there one can say there is a continuity with the older phase, namely that scientific knowledge is still seen as certain knowledge, right? There are no doubts about that sort of knowledge, is certain, but the means to establish that certainty have changed, they have been widened, and the idea that came into European science, European philosophy then was that the certainty of scientific knowledge is established by the scientific method, or scientific methods in the plural. And it's very interesting that there is no clarity whether this is a singular or a plural, which is indicative of some problems, which I'm not going to discuss in detail, but we may come back to it in the discussion period. Now, this was the idea, and that lasted at least to the second half of the 19th century, and then something else happened, and we come to the next phase, and that next phase that lasts until, I think, roughly until the last third of the 20th century, and something changes here. Namely, that scientific knowledge is no longer seen as certain knowledge, absolutely certain, foolproof, watertight knowledge, but it is seen as fallible knowledge. It's not certain anymore, but it can be that it's overthrown in the future, so you cannot be certain that the knowledge you gain in the empirical sciences is knowledge for good. However, there's also an element of continuity, namely the continuity to the phase before, that scientific knowledge is established by the scientific method or scientific methods. So we have an element of discontinuity and an element of continuity, which sounds just right, because if you look at periodizations in history, that is always the case. You have continuities when you have different phases, and you have also discontinuities which define the borders between the phases. But you must always also have continuity, and one shouldn't overlook it. And then we enter the fourth phase, which is a sort of catastrophe. The fourth phase in our philosophical reflection on science starts in the last third of the 20th century, and we are still in this fourth phase. And the main element in this fourth phase is the dissolution of the persuasion that science is a strictly rule-bound enterprise. Rule-bound enterprise, that is what is here, the scientific methods. Scientific methods, or this scientific method, is a rule that must be strictly followed. That's the idea. It came into being, especially by Descartes, who articulated this idea. There are strict rules. These are the rules of method, as Descartes has called them, and his followers, and Newton, and all the other people later, they believed in these scientific methods as rules that must be followed. Now, what happened in the last third of the 20th century was that people lost this conviction that there are these rules, and that was induced by historical studies. Historical studies that try to identify these rules in the practice of science, in the history of chemistry, in the history of physics, in the history of astronomy. And what they found is we cannot identify any such rules. Science doesn't work from rules, really. It works somehow differently. You can still, if you still believe that there is something like the scientific method, just ask yourself the question, why isn't there a book for every science student called The Scientific Method, in which he reads and learns the scientific method in the first year of undergraduate studies? Doesn't exist. If you open a chemistry book, a physics book, a biology book, a geology book, it's not the first chapter, The Scientific Method. Why not? Well, one of the answers to that is because it doesn't exist. Science doesn't work that way. People believed it for a very long time, 400 years, But it seems to be that that sort of scientific method that is supposed to be constitutive of science and of the special character of scientific knowledge, that such a thing simply does not exist. Now, this is a catastrophe, I said. Why is it a catastrophe? Well, it evokes or provokes the question, if there is no scientific method that makes scientific knowledge special, it provokes the question, well, after all, is scientific knowledge really special? What's the difference between scientific knowledge and ordinary knowledge, everyday knowledge, or knowledge of other cultures, traditional knowledge, so-called traditional knowledge, indigenous knowledge? Is scientific knowledge really better? And if you don't have an answer, if that part has disappeared, namely the part of the rules, the scientific method, then the question is, what does make scientific knowledge so special, if it is really special? And that is, of course, the question, what is science? What is special about science? And we are historically in a very strange situation. Our lives everywhere in the world are very strongly influenced by science and technology, and large parts of technology are science-based. Not all of technology, be very careful. Natural scientists don't know that usually, but the technologists know it. Technology has own traditions, but still, large parts of science, technology are science-based. So we are really dependent on science to a degree that has never happened in world history. But now we are at a stage that we don't really know what science is. And I think this is a good job for philosophy of science to do, to confront this question, not only for its philosophical sake, but also for the larger public and also in science education. We've got to teach our students from a very early age, if we teach them science, we should have some answers to the question, why science is special and why it's worth to study science and not something else. Rather believe, say, in evolution and not in creation for some reason. So why is scientific knowledge better there? Just to give you one example. Okay. Now I'll give you a graphic representation of what I just said. Here we have time, of course, in the horizontal line is time. And then in the first phase we have deductive proof as the hallmark of science. And then certainty. Certainty is here is certainty and deductive proof, and we have from minus 400 to something like 600, 1600, we have certainty together with the deductive proof. Then deductive proof becomes, doesn't get lost, but it's really widened to something, namely scientific methods. So we have, you see here that we have continuity of certainty and we have the discontinuity from deductive proof to the scientific methods. And then we have to the next phase. What we get is the scientific methods are here. They continue to the 1900, 1850, 1900. And then people realize the fallibility of scientific knowledge. They realize that begins already, interestingly enough, in the mid-19th century. Physicists especially started to think, well, perhaps science isn't the last word. Our scientific knowledge, classical mechanics, is not the last word. The majority of the physicists, of course, realized that then in the first third of the 20th century, with the advent of special relativity and with the advent of quantum mechanics, which then also led to the unification or sort of unification of physics and chemistry, which is also an interesting prospect. But the point is this. Now we have fallibility. That means knowledge, scientific knowledge, is not absolutely certain. It may change in the further course of history, but its special character is no longer guaranteed by scientific methods. So we are left with scientific knowledge is fallible, and that's it. And that's, of course, not enough. We must know more about science if there is more to be known about science. So that's the historical situation in which I think it's absolutely mandatory for philosophy of science to ask that question about the nature of science again. And especially as my colleague JJ has shown me a very recent article from Nature 3 days ago, we are in a situation, if you look at the so-called science wars, which was a discussion about the quality of science, what science is, between mainly scientists and philosophers on the one side, and social scientists and other people from cultural studies on the other hand. And there is a deep conflict about the nature of science, which is of course influencing also politicians and science funding and science education. And it's very important that we get some clarity there, because as I said, we are culturally dependent on science to an unbelievable degree. So we should really know what we depend on and should understand what we depend on. Okay. Now, these were the historical preliminaries, and now I give you some systematic preliminaries, mainly concerning the understanding of the question. What do I really mean by the question? What is it that I'm asking? Now, first of all, now that may seem that I do that because I got a German passport, but that's not the case. The concept of science that I'm considering here is the concept with the largest possible disciplinary extension. In English, there is no equivalent word for that. It's really fields of research. The German word would be Wissenschaft. The main point simply is what I'm talking about includes the social sciences, the engineering sciences, of course, but also the humanities. So I'm including art history, for instance, which no one in the United States or England would call a science. It's a humanity. It belongs to the arts and humanities. But if you look why also from a say Anglo-Saxon perspective, it's legitimate to pull these things all together, as the German word accidentally does it. If you look at a research university like Harvard University, right, and you look what sort of research is done there, then you find everything there that goes by the name of Wissenschaft or fields of research. It includes, of course, the engineering sciences. In your university as well, I looked at the homepage. I mean, you've got a strong base in engineering and science, but you also have the humanities, philosophy, for instance, and history and other fields, and the languages and literature and so on and so forth. And that is what I mean, what a modern research university like this university has under its roof as fields. That is what the Germans call Wissenschaft, and that is what I'm discussing. I'm asking the question, what is that? Okay. Now, the focus of my question, when you ask what is science, the focus of the question is not completely clear. What I'm focusing on mainly, but not only, is scientific knowledge. So I'm not looking at science as a social system, for instance, interacting with the rest of society, with economy or whatever, with the economy or the military or whatever. This is also a possible focus of the question, what is science, but that's not my focus. My focus is mainly, but not only, scientific knowledge. So I'm asking, what is special about scientific knowledge, especially? Not what is special about the social organization of science, which is also a very important and interesting question, but it happens not to be my question in this talk. Now, a very important point, especially for those who come from philosophy, less perhaps for the scientists who are not so familiar with philosophy, is that in every question you have at least implicitly a sort of contrast. And the contrast I'm having here is I'm asking, what is science in contrast to everyday knowledge? And that is a new contrast, or comparatively new, because in the 20th century, when the question, what is science, was asked, the contrast was mainly a contrast to pseudoscience or to metaphysics. That was especially in the first half of the 20th century, but also longer on in the 60s and 70s. The main contrast, when people asked the question, what is science, they had in mind what is science in contrast to pseudoscience, in contrast to metaphysics. Now, if you know the history of philosophy of the last century, then it's quite obvious that that question didn't lead anywhere. So that no good answer came up about the so-called demarcation of science and pseudoscience and so-called metaphysics. And what I'm doing is I'm going to have a different contrast, and I'm not going to give you the argument now, why, the precise argument, but it'll develop. You'll see that that sort of asking the question in that way gives us some tools for answering the question. I am not dismissing this question. I'm not saying this contrast of science and pseudoscience is unimportant. I'm not saying that, not at all. I'm only saying it's not my starting point. And as it turns out, if one discusses that question, what is then finally the difference between science and pseudoscience, the answer will turn out to be quite complicated, and you will understand then why the original approach, where people approached the question what is science, with a contrast to pseudoscience, why this approach did not yield results. You can't get at this complicated story that's behind that question, as I believe at least, by approaching this question directly, and it's a more productive approach, I believe at least, and I hope I can convince you of that, if you really start from the main contrast of scientific knowledge to everyday knowledge. You may also have in back of your mind, if you come from cultural anthropology, the knowledge system of other cultures, of aboriginals in different parts of the world. They have very solid knowledge that helped them to survive over thousands and thousands of years. So they do have good knowledge. But still that knowledge is different from scientific knowledge. And that is also a contrast you may have in the back of your mind. If you want to, I can discuss a little of that, but that's not the main part of my talk here. And then another thing, again, more important to the philosophers, less for the scientists, a philosopher may say, okay, Hoyningen asked the question, what is science? So he's looking for an essence of science. If you come from Plato and Aristotle, the question of what is X was always understood as a question about the essence of something. And that, of course, presupposes that such an essence exists. And what I'm doing here is I'm asking the question, what is science, like a child? If a child asks, Mommy, what is an airport? The child does not assume that there is an essence of an airport. The child just doesn't know what an airport is. And what I'm doing here is the same. I'm asking very openly. I'm not presupposing that there is an essence of science, but I'm simply saying, look, we do not understand what science is, and therefore I'm asking the question, what is science? Whether the end result will be an essence or not is completely open. It won't be, but that's not presupposed at this point. It would be very unwise to presuppose that, because perhaps we have to really start something new here in order to understand what's going on about science. And finally, there's also a very important point, especially for people who come from analytic philosophy, because people in analytic philosophy love sharp boundaries. Right? Logicians and analytic philosophers love sharp boundaries. And what I'm telling you here is you should not expect sharp boundaries, because sharp boundaries would be a wrong answer. And the reason is this, that there are many fields, or some fields especially in science, where science simply does not have sharp boundaries to other things. And especially there are two areas where you have a transition area to scientific procedures for non-scientific purposes. I'm going to discuss that later a little, where you have scientific procedures for non-scientific purposes, and once you do that, you're not really doing science. You are applying science, but it's not really the generation of scientific knowledge. And even more so in research and development, something your country is quite involved with, if I see that correctly. Less in the fusion reactor, as far as I know, but much more, of course, in earthquake engineering. Earthquake engineering, I didn't study it in your country, I studied it from Japanese, the earthquake engineering, where people try to build structures, buildings that are earthquake resistant. And there is a basic research there involved, for instance, about the basic design. What must be the design of a building in order it to be earthquake resistant, the basic design. What principal materials must you use and other things like that. But then, of course, it's a different story than really to build such a building. And there is, for instance, in Tokyo, there's the collaboration between a bank and the people from the engineering department, and they built the bank in a way that it is earthquake resistant, and they are, of course, putting many measuring instruments into this bank, and this is at the same time a bank that's used for banking and earning money, and at the same time it's a scientific experiment, and they wait for the next earthquake there, and then they look how the building behaves. And there you have a transition area where you can't really say what is now development of a certain product, namely a particular type of building, and what is the basic engineering research. There is just no sharp boundary. You find that very nicely in earthquake engineering, and then also in the science of which probably none of you, or possibly none of you, have ever heard chocolate science. That is a science. There is a book edited by the Royal Society of Chemistry in Britain, and that is called Chocolate Science. And if you look there at the universities who do chocolate science, they do that in the Department for Nutrition, right? They do chocolate research. And you can also go to the great chocolate manufacturers. They have a development unit there. And I went to their web pages and looked what they do. And there you see there is no sharp boundary between what these people do who do development of chocolate, of new products in chocolate with certain aspects, and with what the people in fundamental research about chocolate production do. The same is, of course, clear for car production and many, many other fields. So we should not make the mistake of expecting sharp boundaries of science, especially in the direction of applied research concerning especially the development of products. So any theory that gives you sharp boundaries here is false. So we must have a theory that does not give you sharp boundaries here. That's very important. So if philosophers discuss from the analytic philosophy or from logic, they tend to say a good answer is an answer that gives you sharp boundaries. And I'm saying this is false, because the object is such that it doesn't have sharp boundaries, and therefore the theory about it must not produce sharp boundaries, otherwise it's a bad theory. Okay. Now, these were the preliminaries, and I should now come to the answer. The answer is rather short, as in the title of the lecture, and this is the answer that's going to be explained and defended. It's a very simple little answer. It simply says, scientific knowledge differs from other kinds of knowledge, from everyday knowledge in particular, primarily by being more systematic. Okay? Scientific knowledge differs from other kinds of knowledge, from everyday knowledge in particular, primarily by being more systematic. That seems to be straightforward and simple, but it isn't. I will convince you of that at least. Okay. Now, the program for the talk now, for the rest of the talk, will be this one. I will give you a little history, because that answer is not really absolutely original. You always find precursors, and I'm going to show you a few of them. I will give you a little history of this answer, and also show you that it's not an absolutely absurd answer that some guy from Germany who comes to Asia is now presenting to you, but there is some tradition behind that, right? Then I will qualify the answer, because the answer has to be, it's not quite clear what the answer really says. I have to qualify it. Then, of course, we have a concept here involved that is a little strange, perhaps, systematic and systematicity, and I've got to talk about this concept of systematicity. And then I will first, before arguing for the answer, before presenting the argument why this answer is the right one, I have to make a reflective step before and say, look, what would a good argument look like that you are satisfied with as an argument for this answer? And that is more complicated than you may expect, and that is the reason for that is that looks so simple. This answer looks so simple. I mean, scientific knowledge by being more systematic, that's very simple and you can understand and it's pretty clear. I'm sorry, it is not. So let us discuss that. First, a little history. I have, as I'm pursuing this project now more intensively for the last 9 years, 10 years, but I had the first idea already back in 1980, so I've always had an open eye for systematicity, but I didn't find very much in the literature, and even if you Google or use a Taiwanese search machine for systematicity, then you do not find very much. You find much in linguistics, but you do not find much in philosophy. You don't find it in the encyclopedias, you don't find it, it's just very strange. But still, there is some systematicity in philosophy of science, and I start with someone, John Dewey, in a paper from 1903. I don't give you the context, it's not necessary. He wrote the following. The familiar notion that science is a body of systematized knowledge will serve to introduce consideration of the term scientific as it is employed in this article. It's very strange that he says the familiar notion. He says it's familiar that science is a body of systematized knowledge. Well, I don't know where he has got this from, but he says so. Now, the phrase body of systematized knowledge may be taken in different senses. Now, this will come up in my talk as well. There will be very different senses, more than two in fact. He already noticed there may be two different senses, namely, it may designate a property which resides inherently in arranged facts. That means the scientific knowledge as it is arranged, or it may mean the intellectual activities of observing, describing, comparing, inferring, experimenting, and testing, which are necessary in obtaining facts and in putting them into coherent form. The term should include both of these meanings, the term scientific or systematized knowledge. So what you have here is already that he says something which is similar to my thesis, that somehow scientific can be defined or explicated by systematized knowledge. So this is the oldest trace that I found in the literature, someone having a similar idea than the idea I'm developing here. Okay, here's the next one. Charles Morris in 1960. Don't wonder who Charles Morris is, and if you don't know NORA, it doesn't matter. And he writes about a plan for a so-called Encyclopedia of Unified Science. Also, don't worry if you don't know anything about that. But the point is, when he described something, and echoing Neurath, who had this idea, section 2 was to deal with methodological problems involved in the special sciences and in the systematization of science. Right? That seems to be a goal for an encyclopedia of unified science. The unification of science is the systematization of science. Section 3 was to concern itself with the actual state of systematization within the special sciences and the connections which obtained between them, with the hope that this might help toward further systematization. So there seems to be an idea that systematicity and systematization is something that has something to do with an encyclopedia of unified science, that there must be a sort of system that binds the different parts together. So this is also has something to do with what I'm doing here. It's similar, it's not the same, but it's similar. 1960 that is. Then here's another well-known, famous philosopher of science, Carl Gustav Hempel, and he writes from 1958 onwards, again and again, but never putting much stress on it. In 65, for instance, all scientific explanation seeks to provide a systematic understanding of empirical phenomena by showing that they fit into a nomic nexus. A nomic nexus just means that they are considered to be cases of a law, right? And what you see here, all scientific explanations seek to provide a systematic understanding of empirical phenomena. We also have in everyday knowledge tried to understand empirical phenomena, but the point seems to be that the scientificity, the special character of the scientific explanation is the systematic understanding. And you see the same thought here in Hempel, and you find that also in a later paper, 83, science is widely conceived as seeking to formulate an increasingly comprehensive, systematically organized worldview that is explanatory and predictive. So again, you find something strongly connected with what science is in Hempel here, the point of being systematic. And Ernest Nagel, in a very famous book from 1961, The Structure of Science, writes, "It is the desire for explanations which are at once systematic and controllable that generates science. Systematicity is constitutive of science." That he writes in one sentence. Okay? And here's another quote from the same book. "A number of further differences between common sense and scientific knowledge are almost direct consequences of the systematic character of the latter." That's almost what I'm saying. Right? The main point is the idea of connecting systematicity with science is widespread in philosophy, and it's even more widespread in many, many sciences. I found many quotes where scientists themselves say, physics is just, we have systematic experiments, and biologists, yes, we have systematic ordering of species, and so on and so forth. They say it quite spontaneously. It's not an absurd idea, but the point is that so far no one has really worked it out, what that means and what the implications are. And this is my project. And also what you're going to see, that all these formulations, they are fine, but they are not precise enough. And there's an essential element missing of precision, which I'm going to develop here. Okay? During the last 100 years, it's only one philosopher who really dealt with systematicity. It's Nicholas Rescher. He's from Pittsburgh University. He's a good friend of mine. I've known him for many, many years, but I hadn't read his books before until I stumbled then upon them. He's written more than 100 books. He's 80 now and written more than 100 books and, I don't know, 50,000 papers or 1 million papers. I don't know. His list is just, his vita is like that. It's incredible. Anyway, he has dealt with systematicity, and he has written 2 books on it even. Cognitive Systematization, a systems theoretic approach to a coherentist theory of knowledge. If you're not a philosopher, you won't understand anything what it says, but I tell you, the word system is here and systematization is here. That's enough. Okay, and another book, 2005, Cognitive Harmony, the role of systemic harmony in the constitution of knowledge. And he also means here with the constitution of knowledge, he means, of course, scientific knowledge, and you have also something here, systemic harmony. However, if you look at that more closely, and you've got to take my word for that, then the focus of Nicholas Rescher is different from my focus, because Nicholas Rescher, first he has a different context, is what is called a coherentist theory of knowledge. If you don't know what that is, don't bother. I don't need it any longer. Coherentist knowledge. And he asked why entire knowledge should be put in the order of a system. For him, the term systematicity derives from the noun, from the noun system, the system. Right? He's interested in scientific knowledge as a system, a body that's organized as a system. I use the term systematicity differently, I'm going to show you later. I derive my term systematicity from being systematic, and that's something else. It's much wider than of system. That's a peculiarity of the English language which I'm exploiting, but it is so that Rescher has a different context than mine. So people are close to what I'm doing. It's not an absurd idea, and especially many scientists in many different disciplines have found examples where people spontaneously simply say, when they had to say something about science, yes, it's more systematic than the other stuff of everyday knowledge or whatever, but they don't develop the idea. They take it for granted, and they take it for completely uncomplicated. It's nothing you have to think about, and I think it's worthwhile to think about it and to develop this idea into something that's even worth 2 lectures and to be invited. Okay. Now here are the qualifications of the answer. Now again, the short answer that I gave you is scientific knowledge differs from other kinds of knowledge, from everyday knowledge in particular, primarily by being more systematic, and also by everyday knowledge in particular, and of course, for instance, from traditional knowledge, indigenous knowledge of other cultures, and so on and so forth. But I'm not, as I said, developing this team here in great detail. Now, I must have some qualifications now, because as I said, it seems so clear, but it is not clear what I'm saying in the short answer itself, so I've got to make some clarifications here. Now, first, the terminology. Again, this is a remark directed much more to the philosophers than to the scientists. I'm using knowledge in the same way that scientists use the word knowledge, namely something like good belief, good scientific belief. You can rely on it, it's okay, but you wouldn't let you crucify that in 500 years from now the same knowledge is still around. As a scientist, you would say, no, I don't know, quantum mechanics is fine, but whether in 500 years quantum mechanics is still around, I don't know. But it's really knowledge. I mean, that's the best physics knowledge we have, for instance. So I'm using it in this sense of good, solid belief, but philosophers usually associate with the idea of knowledge, or with the concept of knowledge, they associate truth, right? Knowledge is justified, true belief, and that is an implication I do not want to make, because again, what I'm doing here is I'm trying to presuppose as little as possible. That's very important for philosophical projects, that one presupposes, I think at least, that one presupposes as little as possible, because then one can focus the controversies on what is essential and not upon the unessential things. And I leave it completely open whether scientific, at this point at least, whether scientific belief or scientific knowledge is really true or not. I'm not deciding that, but I'm just making you aware that the word knowledge may be misleading here if you read it as an analytic philosopher or someone in the Platonic tradition of doxa versus episteme, and then you say, oh, Hoyningen talks about episteme, so he believes in the truth of science, and that is something which I leave completely open. And also, the term, that's just a clarification, that's in the handout. You've got an older version, which is not as clear as this one, I hope at least. The term more systematic that's in here, by being more systematic, is not to be understood quantitatively. I'm not saying that there is a measure of systematicity, a number, right? You cannot express it by numbers. And that's especially suggested when I then, in talking or even in writing, sometimes speak about a higher degree of systematicity. Then you may believe that, oh, he means a higher, in numbers, expressible in numbers. But I'm not claiming that. I'm rather talking comparatively. I'm going to elaborate that a little. I mean more systematic, not in a quantitative way. I have no idea whether there is a numerical measure for systematicity, as I have no idea whether there's a general quantitative measure of complexity, for instance. People doubt it very strongly for very good reasons, so I'm not getting involved with that. I'm saying, no, I do not mean that. I mean something else. Then, a very important point, which you can't see yet, the answer is meant to be descriptive, not normative. And that means what I claim is that I describe the actual, really existing sciences. Right? I'm not saying with this answer how science should be. That is not my main aim. I'm saying if we want to understand the existing sciences, including the humanities in this wide sense of science, then this is the way how to go about that and how to understand that, namely, this existing scientific knowledge is more systematic than everyday knowledge. That's the thesis. I'm not saying this is normative, that science should be more systematic. Now, I will have something to say in the end about normative consequences, but at this point it's extremely important to make this difference very clear, as always, by the way, in philosophy, or not always, but in most cases, it's very important that you know exactly what you mean when you claim something. Do you claim something descriptive, or do you claim something normative? And that's important mainly because the arguments for a descriptive claim are very different from the arguments for a normative claim. Right? This is very, very different. If you want to argue that cars drive 50 kilometers per hour in Taipei, right? Then there's a very big difference whether you claim that's empirically true, whether that's descriptively true, or whether cars should drive 50 kilometers an hour as a maximum. And the arguments you need are very different, right? The arguments you need to say, yes, it's reasonable that cars should drive only 50 kilometers per hour in Taipei. They are very different from a statistical survey. What are the average maximum velocity of cars in Taipei, right? So you've got to be careful what you mean. And what I'm saying here is I mean a descriptive claim. That descriptive claim will make much trouble, really much trouble. Therefore, I need the second lecture. Otherwise, I could do with one lecture, but I need a second lecture because it's descriptive, and that makes much trouble. But it's worth it, I think. And now, finally, a very important point here, and that is what I said is missing in the earlier accounts or ideas or sketches of systematicity for science. The answer is comparative in character, and that means that the other kinds of knowledge, especially everyday knowledge, need not be entirely unsystematic. Okay? And this I can show you very simply. If you are interested in how many people are in this room now during this lecture, and you are not a mathematician, you will do one thing, namely counting. You will simply count. You start in row 1, hopefully, or in the last row, and then you count 4, and so on and so forth. which is perfectly systematic. But I tell you, you will not earn a mathematics degree if you are able to do that. Neither in Switzerland, nor in Taiwan, nor in any country in the world. By being able to count, this is an everyday cultural technique that we can do. It belongs to everyday knowledge. It's perfectly systematic, right? But it's not science. So the point is, what I'm claiming really is that everyday knowledge, or the knowledge of other cultures, is not just unsystematic. I'm not saying anything about how systematic it is. I'm only claiming that the scientific knowledge is more systematic than that form of knowledge. That's all. And that's very important, and that's missing in all the other accounts, that I've never seen in the other accounts, and that's a key element that I detected myself only rather late, and not in the beginning. I first also talked qualitatively about systematicity of science. But it's very important to see this point, because it has very important consequences about the dynamics of science and other aspects, and therefore it's very important. Okay? Now, another very important aspect is, before you come up with counterexamples, is that being more systematic in my thesis, in my short answer, is that it refers to knowledge about the same domain. So what I mean, for instance, is the following. You have the situation that we get to know people, right? You haven't seen me before, and now within the last 40 minutes, a picture, or 45 minutes, you have already developed an image of who Paul Hoyningen is. You did that, and we do that all the time. We are social beings, and we do that all the time, and we have our everyday techniques. People look at different things, listen to different things, and so on and so forth. If you compare that, how a scientific way of getting to know who somebody is works, it's very different. So, for instance, if a firm wants to hire a manager, the manager is typically, at least in many firms, is sent to an assessment center. And in that assessment center, this poor manager, or would-be manager, has to run through a series of tests, right? 10 hours or so, a series of interviews, power interviews, and whatnot. And now, if you compare the scientific way of getting to know someone with the everyday way, then our everyday way, it works, of course, to some degree at least, but it's much less systematic than the scientific way. That's the idea, right? So what I mean is, we have to refer here to the same domain, namely getting to know people, and then the thesis says scientifically getting to know people is more systematic than everyday way of getting to know people. That's the point. That's important for the following reason. There is non-scientific knowledge in some domains that is immensely more systematic than some pieces of scientific knowledge. If you look, for instance, in literary studies, then sometimes this knowledge is very loosely organized. I mean, they tell you very loosely organized stories about literature. It's not highly systematic. And there are areas of non-scientific knowledge which are much, much more systematic than that. And here is an extreme example, a very interesting one. It's called VICLAS. It's the Violent Crime Linkage Analysis System. It was introduced by the Royal Canadian Mounted Police, RCMP. Forget it, right? I'm just showing off here. It's just the Federal Police of Canada. They introduced the system because they wanted to identify serial crimes, right? Serial murders. They wanted to identify them. And that means you have 15 murder cases, but you don't know whether they belong into a series by the same man who did it, typically man, by the way, typically a man, whether it was the same man or the way different people committing that crime. So it's a system to identify serial crimes. They are very important to identify them, and because they make much damage and also much publicity. So this violent crime linkage analysis, they link different crimes to each other. And I show you how systematic it is. It works the following. You find that, by the way, if you want on the internet, just Google VICLAS, and then you go to the homepage there, and then you can read everything. I got it from there as well. The aim is the identification of serial violent crimes, and of course the criminals that belong to it. And it works in the following way, that each potential serial crime is catalogued by 262 questions. So you have a candidate for a serial crime, and then you must answer 262 questions about the properties of that crime. And then you build a database, and the database now contains more than 500,000 cases, right? And then the computer tells you which crimes, by identifying the connections, which crimes are candidates for being in a series by the same criminal. That's an extremely systematic procedure. By doing that, much more systematic than many parts of science, but it is not a counterexample against my thesis. Why not? Because it hasn't got the same subject, right? If you compare what humanities do, say, in literary studies, they have a different subject than the subject that is the subject of Weikler's. And the thesis only applies where we do have knowledge of other domains and scientific, where we have knowledge from other areas, everyday knowledge, and about the same subject, scientific knowledge. And for that situation, the thesis says, then the scientific knowledge is more systematic than the other. So it's very important to have that, because otherwise you think, oh, there are many counterexamples, the thesis is just nonsense. It is not nonsense, at least not for that reason. There may be other reasons why it is nonsense. Okay? So, and that, of course, immediately raises another question, namely the question that my answer here is not immediately applicable to areas where science is the only game in town, namely where no comparison with other kinds of knowledge can be made. Now I use an example of chemistry. If you look at the folding of proteins to the tertiary structure, which is, roughly speaking, a protein is a line of atoms, of molecules, and then in order to get its biological functionality, it folds into a complicated three-dimensional structure. And as a biological unit, it works only as that upfolded biological structure. Now, this is a very important problem in biochemistry, also for biology. It's a very important problem in protein chemistry, and chemists are extremely interested in working extremely hard on that problem. The point is now, that's undoubtedly, of course, science. Nobody would ever doubt that this is science. But if you now look at the criterion that I gave you, that scientific knowledge is knowledge that is more systematic than the corresponding knowledge, right, everyday knowledge, then there is no corresponding knowledge. Because if you are not a chemist, or never heard anything of chemistry, you never thought about the three-dimensional folding, or three-dimensional structure of proteins, because you don't even know that proteins exist and that they have a three-dimensional structure, a tertiary structure, and so on and so forth. So it seems to be, when you apply my thesis to cases like that, or for instance to black holes, right? Black holes are exclusively a scientific subject. And there are many more of that sort. Then it seems to be that my answer is not applicable to them, right? And then you say, oh, counterexample, folding of proteins into the three-dimensional structure, Hoyningen is wrong. I know, I told you, the thesis does not immediately apply there, but I can fix that. I got to tell you a longer story, and as I have a few minutes left, well, not so many minutes, but how much time do I have in the end? 60 minutes altogether or so? Oh. For the presentation.
Now we will have about 15 minutes break.
Yeah, sure.
And now we will have a
Yeah, at any rate, so I should rather be finished in about 10 minutes or so. Okay. Now the point is, I can tell you a story about that fixes that. I know it's a problem, but it's not a deep problem. But I better carry on because I want to come to the conceptual issues. So I can come back to it in the discussion if you wish. I'm aware of that, and the thesis is not immediately applicable, but it's not a big problem for an extension of the thesis. Okay. Now here's a very important point. Of course, as a philosopher, if you formulate a thesis, of course you must be clear what your concepts mean. And that's very important in that particular case, because I'm introducing, in a sense, a concept which is, you understand it immediately, but you don't really know what's going on here. So the question really is, what does systematicity mean? What is meant by this term? Now, and it's also very obvious that the concept of systematicity is very vague, and it needs to be made more precise and more concrete. If you want to say what systematicity means, you will run out of steam very quickly, And I'm going to explain to you why this is the case, and there I'm also introducing something which is for the specialists in the philosophy of language perhaps interesting. What I'm claiming here is namely that these two things, to make it more precise and more concrete, are really two different steps. And one has, in order to analyze what the concept of systematicity means or should mean, that one has to make two very different steps that I'm going to present to you now. If you are not a philosopher, you will simply follow me and say, yes, that's plausible, I hope at least. But you won't see that this is important in philosophy of language, but it's okay if you don't see that, why it's important. Now, first of all, I'm starting, and this is a way that is, of course, also deep in the philosophical tradition. If you want to understand a concept, it's quite useful sometimes to ask for contrasts. So what is it not, right? Again, this is, of course, common sense almost. And here are contrasting concepts to systematic. And you see here already, when I speak about systematicity, I mean this is the noun to the adjective systematic. And systematic is what I'm interested in, a higher degree of systematicity, or being more systematic. That's what I'm talking about. I'm not talking about system, really. I talk about systematic. Now, here are contrasting concepts to systematic, and what you find is something, for instance, something that is purely random or accidental is certainly not systematic. Or something that's arbitrary is certainly not systematic. Something that's unmethodical is not systematic. Something that's completely unplanned is not systematic. Something that's unordered is not systematic. So what one may say is that being systematic is to embody some kind of order, right? I mean, this is not very enlightening. It's, I mean, sometimes some kind of order. What is order? Well, it's all pretty vague, right? It doesn't go very far. But what I'm claiming is it is impossible on this abstract level to give more flesh to this concept of systematicity. It is a very thin concept, if you want to say that, if you want to put it that way. You just can't say much more about it if you discuss the concept of systematicity on an abstract level, as I've been doing it here. And what one has to do, therefore, is a second step. And a second step, namely, to make the concept more concrete by giving different contexts in which I want to use the concept of systematicity. And the claim is here, the concept of systematicity will be made more concrete in 9 different dimensions or different contexts, namely those in which I claim that scientific knowledge is more systematic than other forms of knowledge. Okay? So the step is the following. I have a concept that in abstract is very vague. Now I'm claiming I can remove that vagueness only if I tell you the context in which I want to use that concept. And then I'm claiming I'm going to use 9 different concepts and 9 different contexts, and my claim that science is more systematic than everyday knowledge is in fact a claim about that unfolds into 9 different theses. Namely, I'm saying in 9 different aspects, in 9 different dimensions, scientific knowledge is more systematic than everyday knowledge. So the thesis that looks so simple, scientific knowledge is more systematic, is in fact 9 different theses. Namely, depending on different contexts where you use it. Okay? That's becoming more complicated. Now I tell you, that may be very abstract now, but I'm telling you now what I mean is, what I claim then is that scientific descriptions are more systematic than everyday descriptions. Scientific explanations are more systematic than everyday explanations. Scientific predictions, more systematic. The defense of knowledge claims in science, more systematic than in everyday knowledge. Critical discourse in science, more systematic. Epistemic connectedness, that you won't really understand. It's some sort of connections between knowledge, pieces of knowledge, more systematic in science than in everyday knowledge. There's an ideal of completeness of knowledge, which adds a dimension of systematicity. The knowledge generation in science is more systematic than in everyday knowledge. And finally, the structure and representation of knowledge is more systematic in science than in everyday knowledge. Now, what I'm telling you here is 2 things at the same time, and I can't avoid that. First of all, my simple thesis unfolds into 9 different theses, right? And at the same time, the meaning of systematicity, can be made concrete in these different dimensions, but it's not the same in all the 9 dimensions. So I will get 9 different concepts of systematicity. Because systematicity is such a strange beast that in the abstract you can't say very much, you can only say much about it if you have it in a certain context. And I'm going to give you the context, and that has then the result that the thesis, which looks as a simple, unified, homogeneous thesis, is in fact 9 different theses, 9 different claims about the difference of science from everyday knowledge. Now what philosophers now will be very interested in is what is the relationship between these more concrete concepts of systematicity among each other, right? And here is the claim: the more concrete concepts of systematicity corresponding to the 9 dimensions are different from each other. This is more precise than in the handout, and exhibit only family resemblance among each other. The term family resemblance is a technical term from philosophy, namely from the philosophy of the late Wittgenstein. It's developed there in the philosophical investigations. And it means something like the similarity between members of a family. The members of a family don't look all the same, but say 2 of the family have the same nose. Then 2 others may have the same hair. 2 others may have the same size. 2 others, and so on and so forth. You do not find one particular characteristic that they all share. But if you take 2 out of them, they have some similarities. The next 2 have 2 other similarities. The next 2 have 2 other similarities again. So you don't find one defining criteria for the similarity of these members of the family, but you find something that from pair-wise it exists, but it's not the same for all the pairs. So this is the concept of family resemblance, and the point is that I'm making here that the relationship between these different concepts of systematicity that I'm developing here have that sort of family resemblance among each other. Okay, that is, by the way, again for the specialists, the reason why the analysis on the abstract level is so poor in its result. Because if we got on the abstract level already a few defining characteristics, then of course we wouldn't have family resemblance on the abstract, on the concrete level, but we would have a definition to define systematicity for all contexts, but that doesn't exist, and something else exists, namely on the concrete level with family resemblance among the different concepts. Okay? Now it's getting even more complicated. I'm terribly sorry. Now I have already 9 different concepts of systematicity, but it's getting now even more complicated, and it's complicated in the following sense. Even within one single dimension, there are different concepts of systematicity co-varying with different disciplines and even sub-disciplines, and again exhibiting family resemblance only. Now this is very abstract, I tell you. It's very simple, in fact. Look at history, for instance, right? History has look at history and look at mathematics, okay? If you have a description in mathematics that's very systematic, then that means typically that you have an axiomatic description. Right? You can write down the axioms that describe the area of investigation fully, as full as it is possible. If you look what it means in history to have a systematic exposition, say, a very systematic exposition of the history of, what country do I take? Taiwan from, say, 1895 until the present, right? Then the systematicity of this description has nothing to do with axioms, right? It's not an axiomatic description. When historians speak about systematic descriptions, they mean something else than when mathematicians speak about it. So here we have one dimension, namely descriptions, and if you look at the difference then between what different sciences mean by systematicity, you get again different concepts of systematicity, right? That concerns, of course, also the other dimensions. So in all the 9 dimensions, we get many, many more concepts of systematicity, varying with different disciplines and even sub-disciplines. If you look within history, then you can, if you, for instance, consider economic history and compare it with a history of mentalities, then economic history more systematic is more quantitative. A more systematic history in history of mentalities has nothing to do with numbers, typically. Nothing at all, but has to do with more systematic connections to theories in social psychology and other stuff like that. I'm not going into details. If you want to have more details, we have a discussion period in which I can tell you more about it. And it's getting even more complicated, unfortunately, because the concepts of systematicity vary historically. So we have, first of all, a very simple thesis with systematicity. Science is more systematic than other knowledge. Then that spreads out in 9 different dimensions. Descriptions, explanations, blah, 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 and all these. Then when I concentrate just on one dimension, I must say, oh, in different disciplines it's different. And then also in different subdisciplines it's different. And then it even changes in time. So it's becoming very complicated, but that's because science is a very complicated beast. And it has developed for 2,500 years, and it's a very, very complicated body, and therefore, unfortunately, this is so complicated without being, in a sense, overcomplicated. Okay? Thus, systematicity as a hallmark of science does not claim a rigid, unique structure of the sciences. It doesn't say all the sciences are the same. It doesn't say so, because what it says is there's something common to them, that's systematicity, but what that means is really different for the different sciences and in these different dimensions. Okay. Now this presents a problem, and now I have to hurry up a little, how to argue for the answer. Now, the argument for the answer, first we know to some degree what the short answer means, right? Science is more systematic. It means this spreading out in 9 dimensions and in different disciplines. And we know it only to some degree because I have to give you then these different concepts of systematicity. I only talked about them, but I haven't developed them here. I've got to give you the concrete contexts in these 9 dimensions. I've got to explain to you the different concepts of systematicity, which I haven't done, and we have to do so in different disciplines and different subdisciplines, right? Now, the problem is, we have to show that all sciences are more systematic than everyday knowledge in all 9 dimensions, right? That is because this is a descriptive thesis, right? I'm describing the sciences and then I claim it holds for all the sciences. So I must show that all sciences are more systematic than everyday knowledge in all 9 dimensions. And then you may ask the questions, how many sciences are there? Do you know how many sciences are there? Well, don't worry, nobody really knows, because there are very different answers to that. And if you go, for instance, to Thomson's Institute of Scientific Information, that's one of these, the organization that edits the abstract journals, the abstracting journals. And if you look there, then you have in the sciences, in the narrow sense, natural sciences, you have 170 categories, from acoustics to zoology. You have in the social sciences 54 categories, from anthropology to women's studies. You have in the formal sciences 15 categories, from automation and control system to statistics and probability. And in the humanities, you've got 26 categories in the humanities, archaeology to theater, and if you add that up, it's 265 categories. So we have 265 sciences. If you go to different sources, you end up with 400 or even 600. So we have a few hundred sciences. Unfortunately, it's more complicated. It's not my fault. I'm sorry. We have to break up individual disciplines into smaller units because disciplines are not homogeneous regarding their systematicity. I gave you the example in history. If you have economic history, it's a very different subdiscipline in history than art history or the history of mentalities. And they have different ideas what a systematic description is, what a systematic explanation is, what their idea of completeness is, and so forth, and so on and so forth. So we must look at subdisciplines. How many subdisciplines are there? Well, compare economic history, history of mentalities. How many of these smaller units are there? There is almost nothing in the literature. I found one estimates it's 8,530 fields. Right? They are called fields, then, scientific fields, which is a lot. 8,570. That was in 87. So many more now because much has developed in the meantime. And that means I have to defend here and justify something like 70,000 theses right? Which is a lot, okay? Because each of these fields is in 9 dimensions, I claim, more systematic than everyday knowledge. So I got to run through these 8,530 fields and show you for every dimension that it's more systematic, right? I can't do that. I'm sorry. I mean, I'm already now running out of time. I can't do that. This is impossible. And therefore, the question is, how, Paul Hoyningen, do you want to argue for your thesis? Do you want to do that? You can't. So how will you argue for it? And that's, of course, a question. And this is the price of a descriptive thesis. Because the claim is that I'm describing the actually existing sciences, therefore I have this problem, because the sciences are such a complicated body of something like a few thousand different subunits that one can distinguish and must distinguish. Now, the only way is, of course, to argue for the higher degree of systematicity in all 9 dimensions is I will have to use examples. And I have to use examples from different fields, and that is what I will have to do, namely I will have to show that scientific knowledge is more systematic than other kinds of knowledge with respect to descriptions, explanations, predictions, defense of knowledge claims, critical discourse, epistemic connections, ideal of completeness, knowledge generation, and the structure and representation of knowledge, right? That's what I have to do. And I will compare later then the position I'm developing here with other positions that have been given in the philosophy of science recently and also earlier in Aristotle, and then we will see how this theory relates to all the theories about the sciences. But this will be the content of part 2. That will be the long answer to the question, and that will take place on Wednesday, 11th March 2009, which means the day after tomorrow at 2 p.m. And it'll be in this building again, and I thank you very much.